Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers. Because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Forget frequently asked questions,
common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast. Speaking today to Matthew Lungren. He's an adjunct professor. He's in the Department of Biomedical Data Science at Stanford. He's also the Chief Scientific Officer for Microsoft Health and Life Sciences, where he focuses on translating cutting-edge technology like generative AI and cloud services into healthcare applications. So we'll probably talk about some of them and AI in general, and we'll go from there. So welcome, Matt.
Yeah, thanks, Richard. Thanks for having me on.
Well, tell me a little bit about your background and how did your career head in the direction of like translational technology and then AI?
Yeah, I definitely didn't start that way for sure. I was actually an English major, believe it or not, in undergrad, and through a series of kind of, I guess at the time, strange events, I did some global health work and ended up interacting a lot with physicians in that experience, and led me to pursue medicine. But I really thought about a pretty traditional path in medicine, and again, one of those kinds of things in retrospect makes sense, but at the time it didn't. But I started doing a lot of work with population health data, did a lot of global health work and research, and over time gathered quite a bit of data where I needed to draw some insights from that data, right? And I was doing a lot of that work manually. But when I got my first faculty job was at Stanford, I was a interventional radiologist clinician, and then had some research time and kind of wandered over to the Gates building and met some computer scientists and said, hey, I'm a clinician, got, a lot of data sets, and I'm struggling in extracting the insights from those. Do you guys have any ideas? Kind of thing. And they're like, of course we do. Right. So I that was about 2013 or so, right when, AI was really starting to catch on again. So yeah, so from there on, I pretty much ate, drank, slept AI for the last, I guess it's been over 10 years now.
Well, what's happened since 2023? Why all of a sudden, AI has been around in various forms for many, many years. Why all of a sudden is the explosion of ChatGPT and Gemini and, you may not know, but I'm asking all the AI people I've spoken to, what do you think did it? Why was there a tipping point in 2023?
Well, I think that there's a few things that kind of converged at that time, right? So, most of the work that I had done was in sort of the deep neural net work, right? So mainly in computer vision. So how do we use large labeled data sets to train models to do given tasks, right? And a lot of those things in healthcare, there's plenty of examples, but obviously that there was an entire, many decade history of AI before that too. But in fact, the convolutional neural network was first described in the 80s, by the way. But it wasn't until a few factors kind of came into focus, right? So the first being compute, right? Moore's law. For a long time, you just simply didn't have enough horsepower, right, to scale these things up. I think the second big piece was data, right? So you needed to have large quantities of, in this case, digital data at scale. And then I think the final piece was like, what's the best algorithm to learn patterns in large amounts of data? And, there was lots of different versions of this, right? So, go before GPT, we were exploring all kinds of things like LSTMs and RNNs and all kinds of other ways to, in the text and obviously the imaging space both. But there were some sparks that I think when you look back would have better prepared us to predict this moment. I think the first, of course, is that people may know is AlphaGo, right? So this idea of having the model train itself, right? Sort of self-supervised learning. And then the transformer paper, which was around 2017, which is an architecture that is incredibly convenient for scaling. And so all those factors kind of started to blend together, tons of data, really convenient and powerful compute. And then this architecture that's incredibly modular and scalable and able to be self-supervised in terms of how it can be trained. And so I think that, there are lots of different versions of this, but the folks at OpenAI were some of the first to really take that transformer architecture and really scale it up on, internet-sized data sets with massive amounts of compute. And really the goal was to predict the next word. You show it a sentence and you mask out a word, and then you ask it to predict what word was masked out, right? You do that over and over and over again, just like with the AlphaGo experiment, where you just play the game over and over and over again against yourself, right? And eventually you learn patterns, or what we call representations of the information, how it was constructed. And, some folks in one camp believe that internal representation has meaning beyond just the data itself, and then others would argue that it's only learning a certain distribution and can't quote unquote generalize or do things outside of that. I tend to be in the former camp, but nonetheless, those are the ingredients really that got us to this point. There's some other things too, but those are the main ones.
So more data, more layers in like let's say in a neural network, and now novel training methods, and suddenly we're getting this emergent behavior that's working much better than it used to.
Yeah, and the emergent behavior thing is a very interesting topic, because what you're referring to there is that, okay, so how do we judge how these models are getting better, right? Like, so we have to have tests or benchmarks to do that. And there's been lots of benchmarks around forever, certain tasks like identifying or classifying something or translating the, English to Spanish or whatever. There's all kinds of different benchmarks. And what you saw as these models were scaled to really sizes beyond, what folks even thought were reasonable, they were blowing away these benchmarks, but it seemed very sudden, right? It seemed like they were just all of a sudden, boom, it's saturating a benchmark. And that is true, right? They have saturated a variety of benchmarks. At the same time, we sort of feel like it just kind of emerged out of the ether, right, when we talk about it. But ultimately, if you really look at the benchmarks themselves, they're very binary, right? So you either get it right or you get it wrong. And so flipping something from 0 to 1 for a large percentage of the questions, for example, will make it seem like, wow, it popped out of nowhere. It's all of a sudden able to do all these things. Whereas in reality, if you had a more granular, and there's been a few papers on this, sort of looking at that 0 to 1 flip, there's actually a bit more of a gradient there. In other words, there's some more nuance to how these models improve. But what's key to know, I think, for why we're all investing and thinking about this and scaling further, is there's something called the scaling laws, right? Which you may have heard of, or you may have heard of this anecdotally referred to as like sort of the chinchilla paper from Google. But really what this boils down to is that there's these 3 core ingredients in the pre-training stage, right? You've got, like we said, compute, you've got data, and you've got parameters, or the number of layers, as you point out, or the size of the model. Now, those 3 ingredients to make this cake, what they were able to show is that for exponential input in each of those ingredients, you get a pretty smooth linear improvement. So when the model's really not that great, let's just say GPT-2, interesting but not that useful, but there was a clear line that if I just exponentially went up in each of those ingredients with some caveats there, I will get to X performance. And what the investment, all the investment that's been made in this and all the research is really telling us that every time we predict where it would go if we did do that, it has arrived there. So when people refer to the scaling laws and how do we know like that this is worth it? That's what we're talking about for those 3 ingredients. There's other things now that we've discovered too, new scaling laws, as we like to say, but those are the core ones for the pre-training stage.
Well, I know you don't know everything about AI. It's like when you have a friend that knows a little bit about computers, you assume they know everything about it. So I won't assume that with you, even though you probably know a lot. So I know within your specialization, within what you've taken the most time to understand, what model of AI can you describe, in a simple way, how it works? As an example for listeners.
Yeah, I mean, again, you're right. Like I didn't invent any new architectures. I definitely was more of a, again, from being from the medical side of things, trying to learn the technology to the extent that I could both, create new systems and new translations and applications, but also guide the research and the computer science community towards this being a useful approach versus that whole thing. And at a fundamental level, like if you just think about what any AI model in some level is doing, it's learning a function. And what I mean by that is you have an input and you have a desired output. And in the old days, what we would call rules-based machine learning, you would think about the step that you would need to hard code in so that the output comes from that input, right? If that helps. Now, in the deep learning space, all I need to do is provide the input and the output, and I don't need to define the function. The model will, over time, through hundreds and thousands and millions of repetitions, learn the patterns in those layers, the neural network layers, update the weights, as we like to say, right? And it will actually produce that output, and it will do that in some level of performance. That's kind of what we're talking about. So like in other words, even when I was back with my old days, I had all this data and I needed to extract insights, but it needed to be insights that a physician would know. Like for example, reading a clinical note and saying, is this person, should they be admitted to the hospital or not? Let's just take that example. I would have to describe the steps to another human to teach them how to take that note and get that desired output. Well, that's not very scalable, right? Human expertise, et cetera. But if I could have a bunch of examples of the note and then the right answer, I could skip the part in the middle where I have to like write out all the different steps that I think through my head to get to that answer. And I can just feed the data and the labels into a model and it will learn that function if that helps. And so that's kind of the fundamental core of quote unquote AI in general.
You mean you would train the AI once on how you could ascertain whether someone needs to be hospitalized for a certain set of symptoms, and then it would look for patterns in a whole bunch of data where people were or were not hospitalized and what happened, and then you'd have your AI, at least in that part, that would help the doctor, right, the physician.
Yeah, and what's key about this is that that example, let's say I did train a model that could look at a note and decide whether someone should be hospitalized at the same performance level as a human expert, a physician, let's say. When I train that model with that data and that objective, it can do that one thing. It's not going to be able to then write me a poem, right, or help me on my taxes or give me,
or do surgery, or even within medicine, yeah.
Right. So that's what we would call narrow AI. What we are talking about today, generally when we refer to AI, is now generative AI, which is not narrow AI. And the reason there's a big difference is that example we just walked through, I specified the input and the desired output for a given task. With generative AI, I'm not prescribing any particular narrow task. I am, in this case, as I was saying, with these self-supervised training approaches, I'm literally just taking all of the text on the internet, let's just say digitized text, and I'm just predicting the words in the text, self-supervised. So I'm not telling it, I want you to do exactly this task. I'm literally just saying, learn this text of all human knowledge. What's interesting about that is if it's really good, it doesn't matter the domain. So now if I give it that same note that I did in that narrow example, and I say, should this patient be hospitalized or not, there's a chance that the model actually will have a pretty decent performance because it's learned patterns that conform to things that we think about in the world and the way that we communicate and all those things you have to know. So it's fascinating. And that goes back to the idea of emergent behaviors. There's just some things that these self-supervised models are able to do that we all enjoy now today that no one trained them specifically to do, but yet because they learned all of the sort of words and how they work together and how language works and the concepts behind that, we can use them for a lot of useful things.
So through language instead of language, can have papers in it, so you can see the results of direct experimentation. You can see opinions from professionals. You can see, studies. You can see clinical outcomes. You can see all that, I guess, and you have access to it all and look for patterns. So you're backing into a result using, I guess, language or what's been written by countless people.
That's right. That's a really great way to say you're backing into it is a great way to think about it. You're not going in with a specific directive for this task A. You're actually backing into it by saying, just learn all the concepts that we have ever written down, right? And then stitch those together in this massive model.
Okay. So what specific applications have you worked on in the past, or are you working on now that you can talk about, and how did AI help you to figure out, how to get a better result?
Yeah, when I started my career in sort of AI and healthcare, we focused on a very common type of medical imaging examination, the chest X-ray, and 2 billion are done every year. And we said to ourselves, if there's a way to learn the patterns of, dogs and cats and all the great things that were going on with ImageNet, we could probably learn some of the same concepts in a medical imaging exam. So that was actually one of the first things that we did. We were one of the first to describe that AI models actually could learn, pneumonia and, cardiomegaly and other problems that you can find on chest x-rays. Now, over the years, we've translated a lot of that. It led to tons of real applications that are now in practice, et cetera. But what we are now doing in generative AI is a bit different. Here, we're saying we can actually take complex text-based workflows and automate them into some extent from the same model. So, for example, you may have heard of the ambient note solution where you can have a conversation with your doctor and the note gets automatically generated for your doctor. So it saves them a ton of time.
Well, so he doesn't have to sit there typing into the computer. It says a listening, transcribing, or not even transcribing, listening and speech to text, and then no produce.
Yeah, 100%. Right. So think about how hard that problem would be if we went back to those narrow AI days. I'd have to say, I have this transcript and our conversation, right? If you're seeing me as your doctor, we might talk about the weather. We might talk about your cousin's wedding in addition to your knee pain. Now, you have to be able to have the, contextual awareness to look at that transcript and only take out the things that are relevant for the note that I'm about to write. That's a hard problem for those narrow days because think of all the different if-then statements I'd have to think through. If they mention their cousin's wedding, that would be an infinite, things to think about, right? So to make a narrow model to do that. But now, because the model can generalize and think about, okay, well, they're in a context of seeing their doctor. The things that the doctor needs to put in a note are, things related to their knee pain, right? And so that's why you're seeing this big breakthrough on that side. And this applies to a lot of things. Like I have to write a letter to your insurance company to justify medication I'm prescribing, or I need to translate the medical speak jargon into, 7th grade English for patient information, right? So there's these kinds of tasks are now much more achievable because we have a general model that has that text-based intelligence. So it's fascinating. And, there's the lists are miles long of the things that we're doing now with generative AI.
I used to think that you'd have to string together a whole bunch of narrow AIs, and then you'd have a supervisory one that would then take all that information and, give you the answer. And then I thought, okay, well, that's not how it works today. But then what if we add that in? So you have an AI that's listening to our conversation, me and the doctor, and it's using this huge broad base of knowledge. But is there any point for that AI to spin up a series of narrow AIs to analyze subunits of the problem and then take that as another signal of data to make it even better picture, or would that skew it the wrong way?
No, you're hitting on a very, very, very important area. So that general model that might be able to take that transcript and write a note, it may do pretty well, but you could further train it on that task to make it even better at that task with examples like we talked about with the narrow AI days. You can do that same thing even with that big giant model. You can train it on here's a transcript and here's the final note. And what you call it, that's called fine tuning, right? So that's one way to address any gaps in the performance of the model itself. But to your point about narrow models, it doesn't mean that all the narrow models that we've built over the years are obsolete. And when you hear these things, maybe in the popular press, people talking about agents, you have a general model that understands how to have a conversation with, you over text and understands the situation. If you said, hey, I need you to look at this chest x-ray, it might go and run the image through one of those narrow models, to your point, and then bring that information back to me. And that's kind of this agentic, that's when you start thinking about these agentic tasks. So turning the model in from a one-to-one interaction to it's using tools like it's searching on the internet, or to your point, it's going through several steps and realizing I have to use a calculator, or I have to use a different model to get the answer on this particular point. And then I'm going to come back and I'm going to pull all that information together and give it back to you. And that, if you've ever used deep research. Yeah.
The only thing I didn't like is at the time I couldn't pause it and I didn't want to wait 15 minutes and watch the results and be like, oh, wait a minute, that's wrong, shit. And then redo the whole thing over and over and over.
I have heard that. Yes, I have heard that too. Yes. It's kind of like you send off someone on an errand. You're like, wait, no, I also need milk from the store. Shoot, you're already gone. A half hour before you come back.
What about a supervisory, again, a supervisory model? Now it uses narrow AI. It also uses the general one, but then it looks at the results and it controls the fine tuning so that you don't overtune. And maybe another supervisory one that looks at the data you're pulling and make sure, like, I don't know, if the data is not poisoned or skewed in some way. Like, it sounds like you could add in a bunch of like quality assurance type models and, run it using different models. Like what if you put into, I don't know, maybe a crude example, it's a chat GPT and you run every model they have, and then you compare the results and you pick the one that seems to be the most relevant to the answer and then display that. It sounds like a lot of computing power, but I guess for really difficult problems, maybe you need to just throw everything at it. You get narrow AI, general AI, a fine tuning control process, module. I mean, all this stuff. I don't know if that makes sense.
No, it does. And there's a few concepts that you're hitting on. Like, it sounds like, just organically here, but these are very real. Exactly. So, if you think about a really complex problem in healthcare where you have like images and you have text and you need to figure out if that patient qualifies for clinical trials, and then you need to figure out what the research is, you have a series of tasks. To your point, you can have a supervisory model that you're interacting with. You say, hey, can you process this information and bring me back everything I'm going to need to know to take care of this patient? Well, it's going to set off a series of subtasks. And some of the subtasks, to your point, might be other models that have been prompted a different way or fine-tuned a different way, right? Some of them might be those narrow models we talked about. Some might be just organic search. But the idea that you also have about having a supervisory kind of checker is a very popular one. And again, yes, you would have to use a lot of compute, but the other factor that's going on in addition to the models getting smarter and smarter much more frequently is also that the cost is going down. So even some of those things that you're like, that's a little much, right? It would take too much compute or too much time or whatever it is. It's very rare that that's a barrier to trying something out, because we kind of anticipate cheaper, faster models anyway at the same level or better intelligence. But the last thing you mentioned, which is like provide several answers and then judge which one's most likely to be correct, that's something that you can even do with one model. You can have it answer it 10, 15, 100, 1,000 times and look at that distribution and say, it's saying this one answer way more often than the others, so this is probably the right answer, right? So there's all kinds of tricks like that. It's a fascinating area. Like, there's thousands and thousands of papers just in the last couple of years, just on these kinds of thoughts and concepts.
Okay. So again, what's like a very particular thing you've been working on, a medical device or a medical application that, is getting good outcomes? Like, how did you use AI in it? Let's talk about a case study if you got.
Yeah, we talked about sort of the ambient note solution a bit, which is, already now being used by, more than 500 health centers. Billions of lines of clinical notes are being written every month. But something that my team is focused on is, we've just talked a lot about how great the models are in all kinds of different medical applications. You've seen the headlines where, they do better than doctors in certain areas and all these other things. There are areas where it's not so awesome. And we go back to other types of medical data that's not text, right? So we know these models can look at images, right? You can put a picture of, your backyard into GPT and ask it how to, furnish with new patio furniture, whatever. And it does pretty well. But if you put your chest x-ray or an MRI or a pathology image into GPT, it knows what the medical concepts are. It just can't see them. And so what we've done is we've actually built a variety of vision models that can be connected to the big general reasoners and do very interesting and great things. So one thing that we've done is we've created a system where you can put in an x-ray and the model will write a report just like a physician would. And the reason that's interesting is that just like in that case where you go to your doctor and you talk about your problem and then the note's ready, if you take the analogy there, it's like instead of a transcript, this time it's an image that gets turned into a note for the doctor, and the doctor can edit and sign it. So that's actually where we've spent a great deal of time. We've just launched several different models with this capability. And what we're really trying to do is augment the clinical workforce writ large, right? To be able to have more time to take care of patients and less time doing some of the paperwork that we do. And some of that is writing notes. And it's a powerful unlock, and it can't come at a better time.
I thought of an application, like you have a blemish or something on your skin, you take a picture of it, you put it into a tuned AI system, and it looks at millions of different skin blemishes, and it says, okay, okay, I've scored it. It looks like you should see a dermatologist about it. Would you like to see one? They could send the image over to them and blah, 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 So it's not practicing medicine, but at least it's a screening mechanism to tell people, hey, this is something you should look at, or, there's a low likelihood it's a problem. I would just leave it.
Yeah. I mean, so there are applications that are, currently available, right? That do this. And then, so this is clearly a narrow AI use case, right? But remember that as we start to get to the consumer side, meaning now we're actually giving this to the hands of folks to potentially even self-diagnose. That's an incredibly challenging / very much a regulatory space. Because the 1 or 2 times out of 100, or even 1 or 2 times out of 1,000 that it's wrong, if the average consumer may not have the medical training or background to appreciate the possibility that could be wrong, and so there's a lot of complications in there. But your North Star vision is correct. In other words, today we're seeing consumers, patients putting their medical data into these models, having conversation with them, and they're getting tremendous value out of that. And sometimes even finding things that physicians have missed, which is really, really critical. But remember that the models like GPT that you use on your app were not designed for that. And therefore they're not saying, hey, use this and you'll get this benefit. Now, if you said, oh no, I've got this dermatology model and it does XYZ, well, now you're making claims that may be true, that this model can do that. But then you have the burden of proof in order to be able to market that to everyone, that it has a certain performance level that meets regulatory requirements. And that's where it gets really tricky. There are approved apps for things like taking pictures of skin lesions, et cetera, but there's a lot of complications there when it comes to health. And that's why we're in a very much let me find the low risk, high value things in healthcare that I can absolutely do today and start doing those. In the process, starting to do the work to get to the higher risk, high value use cases in the future.
I mean, people are going to do it. I've spoken to a number of people that say, they're using ChatGPT as a therapist or to solve, what do I say to someone that's upset me about XYZ, or, people are going to run way ahead of this thing. I don't know. I guess it'll be a race to have AIs respond or not respond in the right way. Meanwhile, other people developing applications that, you can really insert forms so that regular folks can use it.
That's right. No, you're right. And that this is the, kind of the knife's edge of the cutting edge of capability. There's never been a time when anyone on the planet with an internet connection had easy access to some of the most powerful AI in the planet, or the most powerful AI. And this is a completely unprecedented space that we're all in. It used to be that you could go on a Google search and search for health info and, gather a bunch of information, but it still was tough. Who you would trust? What do these words mean? It gets really, but now you can, like you're pointing out, you can have a pretty average conversation with a model and get incredibly good information back about very complicated topics like healthcare. And I encourage it. I mean, I think that folks should be able to educate themselves and reduce what we call the information asymmetry between different disciplines. At the end of the day, having a clinician that can sort of act on the behalf. So there's the knowledge part, but then there's also the doing part. And I think we're getting the knowledge part pretty democratized, but then it's like the doing part. So what is the action that you take? And that's when things, I think, start to get into a place where we partner with the patient, the doctors and patients partner, and decide what the best treatment is.
Yeah, it's crazy. In healthcare, in the area you're in, what do you think are going to be some of the next big advances that we're seeing, in the clinic in the next 2 years?
Well, I can certainly say that there's going to be a lot of AI. What I usually say to this kind of a question is that even if we froze time and the technology doesn't ever get better from where it is, which is we all know is not the case, it's going to save a massive amount of time and probably an equal number of lives, given all the places in pharmaceuticals and med technology and, as you point out, in patient education and patient interaction, and then obviously physician time savings and an insurance company. There are so many places that have very ossified manual things that very highly educated people are doing that can be reduced. The burden of that can be reduced significantly. So I do anticipate a future where a vast majority of particularly the administrative things that we do, which, believe it or not, make up a ton of the spend and potentially even the waste in healthcare, will be tackled. Beyond that, what I would like to see, and I'm somewhat of an optimist, is that as these models get better and better, I would like them to help guide the new discovery of better treatments, right? Precision therapy for a specific disease that has no side effects and, is extremely effective. Like all of these other things, these North Stars that, we all spend literally careers working on, could these models help us do that as well? And again, I'm optimistic in that we're going to be able to leverage them for science and discovery. And again, that's sort of the utopian vision of this all. And I have to believe that we can take a crack at it.
Okay. Well, very good. What's the best way for people to follow up on your efforts and other people in your field, like that are advancing medicine? Where can people go to, get a general view, and where can they go to follow specifically what you're doing?
Well, first I'll say that if anyone wants just to learn more about AI in general, I would definitely recommend deeplearning.ai, which is there's a series of courses. You don't have to have any coding background. It's done by someone named Andrew Ng, who's a very famous computer scientist and one of the founders of Coursera, if you know that platform.
Yeah. I took one of his courses on Coursera years ago. Yeah.
Phenomenal, right? He's an unbelievable educator, and I encourage everyone, I don't care what you do for a living, it is just a really wonderful way to get up to speed. All the things that we've discussed today and even more. For folks interested in healthcare AI, you can follow me on LinkedIn, clearly, right? I tend to post a lot about this. There are people that I like Eric Topol, who has a Substack. He's a physician and technologist. He has several books. The most recent is Deep Medicine, another phenomenal voice, very down to earth, very easy to digest, and really tries to separate the hype from the reality. And then I also have a course on Coursera that if you really want to get a little bit more into the weeds on some of the technical stuff behind the scenes, we have one on the fundamentals of machine learning in healthcare that will definitely qualify you to work in my field and hopefully come up with even more discoveries than we have today.
And last thing, does anything scare you about what's possible just in the medical realm, not AI in general, but there?
I mean, there is the part that is, not all AI is created equal, and we tend to have a tendency to generalize with broad brushes. And what I worry about is a bad outcome because of an AI system that was used that kind of sets the whole field back a bit, if you see what I'm saying. So the analogy is like in the self-driving car world, we know it's, there's opportunity. We know the technology is getting to the place where this is really safe and effective, but a couple missteps can really set the whole field back. And so far, I think we all are, because we all have access to it, I think to some extent we have a very sober view of where the models are great and where they're not. But yeah, that's probably what keeps me up at night if I'm being honest, because there's so much good that we can do, but it definitely requires we do it thoughtfully and responsibly.
Okay, fair enough. Well, very good. It's been a very cool call. I enjoyed speaking to you, and I think you're a very good communicator, and thanks for being here.
Yeah, thanks, Richard. This is great. Appreciate the opportunity.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.